So energy in the form of heat added to a metal to change to liquid. Crystal growth start at surface. So while cooling, it is starting on the surface. In case of casting, the heat is being given up to the mold material in contact with the outside of the molten mass, and then because the freezing temperature will be outside of the liquid. Inside it will be hot. Second phase is slower. After formation of solid skin, grain growth is likely to be more orderly, providing the section thickness and mass at large enough to cause a significant difference in freezing time between outside cell and interior metal. Second phase also directional from one side because it is from outside to inside. So heat added at a constant rate, melting temperature reaches, and the liquid temperature reaches. Then it go down when heat is removed at constant rate, the solidification temperature, and then go down to 0. Heating and cooling of temperature increase of the melting point of a metal. Third phase, as well as thickness of frozen metal increases, the cooling rate of the remaining liquid decreases even further, and the temperature of the remaining material tends to equalize. Grain characteristics influenced by cooling rates. The first grain form around the outside of the equiaxed, fine equiaxed. This one outside cell, fine equiaxed, then columnar grain. After this is the hottest part inside, so it will slowly cool and coarse grain equiaxed. Typical grain structure for a solidification of a heavy section. Schematic sketch of a dendritic growth. So even if it is this like same. Eutectic. Similar to pure metals, eutectic alloys freeze in much like pure metal. It is because it is pure metal. By definition, a eutectic alloy is one temperature, means single temperature to liquefy. But non-eutectic freeze through a temperature range. The majority of products are made from non-eutectic alloys. Instead of freezing at a single temperature, as do pure metals and eutectic alloys, non-eutectic alloys freeze over a temperature range. Start of freezing outside mossy stage and process of freezing that is given. Okay, there is segregation. Dendrite grain growth is much more evident in the non-eutectic alloys metals than pure metal. When more than one element is present, segregation of two types occurs during the solidification, which is not good. The change causes the ingot type segregation is small, but as the first solid drop to remaining material, a gradual change in composition occurs as freezing progress to center. Because it should be alloy, but it is divided into two parts. So segregation is not so good for casting. Quality of casting products. One technician might define quality as tighter dimension tolerance. For one, casting increases strength. For another, increase corrosion resistance. For a maybe for a third. So that is the quality, but as it is given by your specification, you are assuming that. Surface finish and internal quality of castings. Metals are superheated above their melting temperature to increase their fluidity and allow for heat losses before they are in their final position in the mold. For good casting, the metal must be at correct superheat at the time it is poured into the mold. If the temperature is too low, misrans and cold shots will show up as discontinuities in the casting. The metal may even freeze in the ladle. If the temperature at pouring is too high, the metal may penetrate the sand and cause very rough finish on the casting. Pouring temperature that is too high may cause excessive porosity or increased gas development, leading to voids and increased shrinking from thermal gradients that disrupt proper directional solidification. So typical discontinuities, porosities, gas holes, hot tears, cracks. Because you are from NDT, I am not going to too much for these defects. Shrinkage cavities, air pockets, and cold shots. Okay, I will just show you for the casting porosity. There is gas holes or gas holes. Yes. Can you please mute yourself? So inclusion, hot tears and cracks. See. So inclusion, hot tears. Hot tears at the corner. Casting is not, design is not good for corners. If corner is there, it will crack. This is the corner cracks. Hot tears. While hot, it will crack. Crack inside is crack. Shrinkage cavity, air pocket, and cold shot. Where is cavity? Here also. You can say shrinkage cavity, and this is something shown as cold shot. Let us see what are they. It is not so much. The future of casting, continuous improvement. There are two cold sets. I already explained you. One is SHOT and SHUT. Belu Chinna. Mr. Belu Chinna. Belu Chinna. Hello. Thank you. So metals are separated above their base before they are in final position of the mold. If the temperature is too low, mistrans and cold shots will show up. So this is because it is pouring from one side or from two sides, so it will not match at the center because it is too cold temperature. That is called cold shot. And for cold shot, it will just stick something outside the casting. Cold shots are a result of turbulent flow. Drops of splashing metal lose heat, freeze, and are then entrapped as a globule that do not join completely with the metal. So there are different things.